Okay, let's take a look at today's lesson. What we're going to be looking at today is called partial fraction decomposition. Let's talk about why we might want to learn something this fun. And it is fun, okay, to me, okay, probably maybe to y'all. So when we deal with fractions, our norm is to find a common denominator and add them together. That's what we normally do. This is actually reversing the process. We're actually going to take a fraction that's all put together and we're going to break it apart into little pieces. And the reason that we would do this actually has to do with Calculus 2, BC Calculus, the second part of BC, is this in order to integrate. This is one of the techniques where a student would need to know how to do partial fraction decomposition so you can get little bitty fractions and integrate the little bitty fractions. Way easier than integrating a big gigantic fraction. So this technique, and actually, strangely enough, I just taught this partial fraction lesson to the BC Calc guys last week. We just did partial fraction integration last week. So we're going to spend 2 days on this. Today is the only day with notes. Tomorrow is just going to be more practice on this. So let's kind of go through the steps. If this works, we're doing a fraction. N's the numerator, D's denominator. The very first thing that we would do in a situation like this is divide if the fraction is improper. Now improper, you're used to thinking, well, an improper fraction will be like 9 over 4, right? The numerator is bigger. The difference with this that catches students sometimes, and that's true, it has to do with the degree. Here's what we're looking at. If the degree of the numerator is larger than or equal to, the or equal to sometimes is what catches students. Like if it's x squared something over x squared something, that's improper. We need to divide it. We need to do long division. So if it's improper, we're going to use long division to basically divide it out. The remainder is what we're going to do partial fractions on. So we did long division just, a week or so ago. We practiced long division. We have our long division, we do this, we get whatever, x plus 1, get down to the bottom, maybe our remainder is like 7x plus 3. Remember we put the remainder over the divisor? Remember how we wrote that? That's what we would do partial fractions on. If we had one like this, where we had to do the long division, we would do partial fractions on the remainder, because this part's going to be whole. So and we have an example like that on the daily work for you to practice. So that's our first step, is to look to see if it's improper. If it's improper, we're going to divide it. Our second step is going to be to factor the denominator completely into linear and irreducible quadratic. That's a vocab word we learned, right? Irreducible quadratic would be like x squared plus 4. That would be, if we kept factoring, we would go into imaginaries. That's what an irreducible quadratic is. So that's our step 2. Now, once we get it factored, we've got to break the equation apart, break the expression apart, the fraction. We're going to put it into little pieces. So I'm going to give you examples of just how it's broken apart right here, just so that we're clear. So, for example, we are either going to have a linear factor or a quadratic factor, or a combination. So, one example, let's say you have, x plus 2, you factored it to get x plus 2, x minus 3. Say we just factored it to get that. When we break this apart, a linear factor is going to have just a letter over it, whatever letter in the alphabet. So we would break this apart to be a over x plus 2 plus b over x minus 3. Now there's a whole lot other stuff we're going to do to this process. I'm simply demonstrating to you how to break it apart. There's a lot more we're going to do, so don't think that this is it. A student was like, well, what about the numerator? We're not there. I'm just talking about breaking it apart. So one thing, too, sometimes, say you're working with a partner, and your partner put the x minus 3 first and the x minus 2 second. You got those reversed. So your A's and B's are different. That's okay. That's not a problem. We're going to come out with the same answer in the end. It doesn't matter what order you put them in and which letter you put over it. The end answer will be the same. All right, so that's what we would do with the linear factor. This portion is talking about a repeated linear factor, So for example, an example of a repeated linear factor, let's say we have something over, I don't know, x minus 1 squared. Okay, this is a linear factor. We see it's to the first power. The factor is linear, but it's repeated. The repeated have to be basically this pattern. That's how we have to expand them, was this pattern. That we would do a over the first one plus b over this one squared. If this were to the fourth power, let's say it was x minus 1 to the fourth power, then I would need to say plus, this would be, to the first power to the second power, plus c over x minus 1 cubed, plus d over x minus 1 to the fourth, and so forth. For repeated factors, we have to break them apart that way. All right, so that's if you have a linear factor. What if we have a quadratic, an irreducible quadratic factor? What do we put over it? What do we put in the numerator for those? Well, an example of that would be, say, something over x squared plus 4. That's a irreducible quadratic. So to break that apart, we would do ax plus b over x squared plus 4. Okay. Notice the pattern. If I have a linear factor, I'm just putting a single letter over it. If I have a quadratic factor, I'm putting a linear factor over it. Or it's not a factor, but a linear binomial over it. Okay, so that's just what we do. That's how we expand it. Now, what if I have a repeated quadratic factor? What if I have something like, I don't know, like x squared plus 1 squared, or cubed. Let's do a cubed. How would I do that? Okay, so we would break that apart to be ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared plus, and then ex plus f over x squared plus 1 cubed. And those are just examples of the expansion. How do we expand the big fraction into little bitty fractions? That's the patterns that we use. Okay? Questions on that? Okay, well then let's go to the next slide and let's just kind of jump into some examples. Okay, so we look to see first whether it's improper. This is squared, this is cubed, this is not an improper fraction. We don't need to do long division. We really need to always look at that first. Okay, so we don't need to do long division. Second step, we're going to have to factor, and this is kind of a lengthy process. You might want to write down steps for yourself. So the first step, we check to see if we need to divide, if it's improper. The second step, we're going to factor the denominator completely into linear and irreducible quadratics. So we factor the denominator, I'm just going to put my little scratch work down here, x times x squared plus 4. So I have a linear factor and I have a quadratic factor. Okay, so now I'm going to break it apart into little fractions. So this is equal to x, which would have an a over it, a over x, plus bx plus c over x squared plus 4. Okay, so notice how I'm setting this fraction equal to the original fraction. My little fractions are breaking apart are going to be equal to the original fraction. Okay. Once we have it expanded, now again, your friend that you're working with, they may have reversed these. They may have put the x squared plus 4 first, which would have ax plus b over it, and this would have a c over it. That's fine. That's not a problem. We're going to get the same answer in the end. Okay, the next step, we're actually going to multiply. We're going to clear the fractions. I'm going to take my denominator, x times x squared plus 4, over 1. I'm going to multiply by this denominator, and it's an equation, so I can do whatever I want, right? I can multiply by anything I want. I'm going to distribute this to each of those fractions. I'm going to multiply it times all of those fractions to clear the denominator. We're going to clear the fractions out. So when I multiply this times my original fraction, I just get the numerator, 2x squared minus x plus 4. When I multiply this common denominator times the first this a over x, notice this has an x and this has an x. So I'm left with a times x squared plus 4. Okay. Then I do my last multiplication. I multiply this times this last fraction. This has an x squared plus 4. That has an x squared plus 4. They cancel. I'm left with bx plus c times x. Okay? So that was our next step. We cleared the fraction. We multiplied by the common denominator. Now what I'm going to do, and you know, this is a step that as you work through these, you may not have to do this. I'm going to go ahead and just distribute this out and clean it all up, just so we're clear. So the left side is 2x squared minus x plus 4. The right side, I'm going to have ax squared plus 4a. Then I'm going to distribute this x, so plus bx times x is bx squared, and c times x is cx. Okay, is everybody okay? So what I'm going to do now, it's like some SAT problems are worked this way. It's like a very abstract kind of thing. What I'm going to do, we know that if this side, this equation is equal to this one, or this expression is equal to this one, we know that the x squareds, their coefficients are going to have to be equal. Right? They have to be equal. So, in other words, I'm going to set up a system of equations that I'm going to solve to find a, b, and c. That's what we do. So, let's do that. So I have this x squared, so it's going to be, I'm going to take the 2 and I'm going to make it equal to 2 equals, and then I need to pull out the coefficients of the x squareds over here. This coefficient of x squared is a plus this coefficient is b. And so now I'm done with those. So I'm going to pause here for just a second. Some students get really confused on this part and want to include the x squareds. That's not the goal here. We simply want to equate the coefficients to each other, not the variables. Because we're going to use this as a system of equations and we're going to find out what a, b, and c are. Normally what I do is I just put these in like a little bracket, little parenthesis thing. Just so that I know those are my systems of equations that I'm going to solve, and then I'm going to have work, you know, and then I'll have my answer. So that's where we equated the x squared coefficients together. Now let's work on the x coefficients. This coefficient of this x is a -1 equals, we're just doing equals. I only have one over here at c. Okay, so we took care of that one. The last one that we want to work with is the constant. On this side, the constant is 4. Over here, it's 4a. Basically, on this side, the constant is anything that doesn't have an x. That's the constant. Now, I just want to give you a what if. What if my numerator didn't have an x squared term? What if it, because sometimes they don't. What if it didn't have an x squared term? Well, I still have x squareds. I would need to do 0 equals a plus b. Right? You with me? So if the numerator doesn't have the term you're looking for, then that is 0. 0 equals whatever we have over here. All right, so this is a system that I'm going to have to solve. Usually they're fairly they're not really difficult systems. In fact, we already know what c is, right? C is -1. And just looking at this, we can see what a is, right? There's not really much work at all. A is 1. Now to get c, B, we'll just back substitute into this equation. So let's see, 2 equals 1 plus b. So b is going to be 1. Okay, so those are our coefficients. The very last thing that we do is we write out our partial fractions. So I'm going to come up here. I've got, so a, so it's 1 over x plus, let's see, b was 1, so x, and c was -1, so x minus 1 over x squared plus 4. And those are the partial fractions. That's what we would integrate next year. And really for this technique, the longest part is the partial fraction decomposition. Once you have it broken down, the integration is very easy and quick. So it's really to your benefit to know this technique next year, so that you're going, oh yeah, I know how to do partial fraction decomposition. That's fine, not a problem. Okay, imagine facing this lesson in calculus and not knowing how to do this. That would be a bit of a problem. All right. Okay, our very first partial fraction decomposition. We doing okay? Okay, let's go to our next one. So this would be x squared, and that's x cubed. It's not improper. We don't have to divide. It's actually already factored for us. And we are just fortunate to have a repeated linear factor. It's repeated 3 times. So we're going to have to break this apart. This is going to equal a over x plus b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. Okay. Once I have it broken apart, Okay, so yeah, let's talk about that. So the cx plus d, the ax plus b, those are over irreducible quadratic factors. Irreducible quadratic. This is a linear factor that's simply repeated. The factor itself is x minus 1. That's the factor. That's linear. And it's simply repeated. It's repeated 3 times. So no, we just need single letters over this. Okay? So once we have this broken apart, we're going to use the same procedure we did before. We're going to multiply by the common denominator. Multiply everything by x times x minus 1 cubed. So this is going to be distributed to all of the fractions. I mean, every single one of them. Okay, we're going to multiply it all. Our goal is to clear all the fractions out of the way. So when I multiply, I just love multiplying by the original fraction. That's so easy, right? It's just going to be the numerator, x squared plus 1 equals. So let's multiply the common denominator times this. So I have an x here. That x would go away. So I have a times x minus 1 cubed plus. The b fraction, I have an x minus 1 there, so I'm going to need the x, and I'm going to need the x minus 1 squared. For the c fraction, I have x minus 1 squared, so I'm going to need the x and one of the x minus 1s. And for the d fraction, I'm just going to need the x. Is that okay? So here, yes, that's x minus 1 cubed, yes. If you don't remember binomial expansion from last year, really that would be a very great thing to know here, so you don't have to multiply x minus 1 times x minus 1 times, FOIL all that out. Binomial expansion, does that ring a bell? Pascal's triangle, the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Oh, yeah. Yeah, that's where it comes in. I remember it, so I'm going to use it. If you don't remember it, you're going to have to multiply them all out. So the coefficient for this is going to be 1, 3, 3, 1, right? So x squared plus 1 equals, so plus a times, so I'm going to get x cubed minus 3 minus 3x squared plus 3x minus 1. That's what you would get with binomial expansion, or if you multiplied it all out, that's what you're going to get. Plus. Here, this is easy for us to do in our head, right? To multiply out x minus 1 times x minus 1, that's going to be x squared minus 2x plus 1, right? And distribute the x to it. So it's going to be x cubed minus 2x squared plus x plus c is going to be times x squared minus x and then plus dx. Now there will come a time when you don't have to do this next step. I'm going to go ahead and do the next step just to be so we're clear. I'm going to go ahead and distribute the a, b, and c to get this all multiplied out. So I have an x squared plus 1 equals. So we have an ax cubed minus 3ax squared plus 3ax minus a. Okay, so that's distributing the first one. We go to the next one, plus bx cubed minus 2bx squared plus bx, plus, we go to the next one, cx squared minus cx plus dx. Alright, now we are ready to set up our system of equations. So the largest exponent here that we have on the right side is cubed. I need an equation with cubes. Do I have a cubed coefficient? No, so it's going to be 0. 0 equals. 0 equals. So let's pull apart our cube. So I have an ax cubed, so a, so that's gone. Let's find another. Then I have a bx cubed, so plus b, so that's gone. And those are all the cubes that I have. Okay, now let's go to the squareds. I do have an x squared in the numerator, so 1 equals. Now let's pull out all the squares. So I have a negative 3a, that squared's gone. Let's keep going. I got a negative 2b, that squared's gone. And then I have a plus c, and that squared's gone. So everyone see the pattern what I'm doing here? I'm just collecting those coefficients. Now the x's, I don't have an x term in the numerator, so that's going to be 0 equals. So x, I have 3a, that one's gone, plus b, that one's gone, and then minus c, and then plus d. Okay, for the x's. And then for the constant, I have a 1 equals, let's see what constants we have. Negative a. We have any others? Nope. So that's the system of equations that I need to solve. Okay. We can do a like in our head, right? A is going to be negative 1. Okay. I'm going to back substitute here. I have a plus b is 0, so you can do that in your head or you can write it out. So we have negative 1 plus b equals 0, so b is 1. Again, we're going to back substitute. I have a and b, so I'm going to put those in this second equation right here. So 1 equals negative 3 times negative 1 minus 2 times 1 plus c. So c, what is that? 3 minus 2 is 1, so c is 0. Okay, that's interesting. C is 0. Okay, we can do that. Last one, let's find d. We're going to have to back substitute into this third equation. So 0 equals 3 times negative 1 plus 1 minus 0 plus d. Let's see. 3 times negative 1 is negative 3. Negative 3 plus 1 is what? Negative 2. So I move that over, so d is 2. Alright, so let's put those numbers in our fractions. So I have negative 1 over x plus b is 1, 1 over x minus 1. The c fraction, that's 0. That means that wipes out this entire fraction. We don't have that fraction anymore. It's gone. 0 over anything, well, except 0. 0 over x minus 1 squared is 0, so that fraction's gone. Alright, then the last one is d. d is 2, so 2 over x minus 1 cubed. And that would be quite easy to integrate, those little pieces, versus this would have been pretty much impossible. Okay? And that's partial fraction decomposition. How are we doing? Okay, it's algebra, like tons of algebra. It's fantastic, right? Oh, I love this.